Welcome to the second part of the problem-solving session for Chapter 26. We begin where we left off in question 6. Here we're given a combination of capacitors connected to a 12-volt battery, and we're asked to determine several things. Let's go ahead and make some small repairs here to our diagram. So we have capacitor C1, 4 microfarads, C2, 5 microfarads, C3, 6 microfarads, and C4, 10 microfarads. Well, the first question that we're asked to determine is the total capacitance. And what you see here is that we have a combination of capacitors in series and capacitors in parallel with each other. So what should be our approach in this case? The first thing we try to do is to work from the furthest, the outermost capacitors in closer to the battery, in other words. So what we see here is that both C2 and C4 are in parallel with each other because the potential difference across the plates, C4, is the same as the potential difference across the plates of C2. There are no capacitors in between. So we can say that C4 and C2 are in parallel, and so C24, the combination of C2 and C4, is just the straight sum of C2 plus C4, and again, that's because these are in parallel, which gives us 5 microfarads plus 10 microfarads is 15 microfarads. So what does our circuit look like once we have done this? Well, let's see. We've got our battery. We've got our delta V total. We've got our C1 here. We've got now the combination of C2 and C4. So it's as though we have one capacitor C24 and C3. Now you can see that in this arrangement here, C1, C24, and C3 are in series with each other. So to find the total capacitance, we must sum the reciprocals first. C1234 will be 1 over C1 plus 1 over C24 plus 1 over C3. We plug in our numbers, and we have 1 over 4 microfarads plus 1 over 15 microfarads, what we just found, plus 1 over 6 microfarads. Well, I prefer to work with fractions, so I find my common denominator 60 microfarads, and so I get 15 plus 4 plus 10, which is equal to 29 over 60 microfarads. Well, that means that C1234 is equal to 60 over 29 microfarads, or 2.07 e to the minus 6 farads. So this answers part A. In part B, we're asked to determine Q total. This time, Q total is no different than before. That is C total, 1, 2, 3, 4, divided by delta V total, that of the battery. When we, it's not divided by. Let's just make a little correction here. It's multiplied by. So let's try this again. So Q total is C1234 times delta V total. And that gives us a product of 2.48 e to the minus 5 coulombs. In part C, we're asked to determine the charge on each of the capacitors. When we come back over here to this arrangement, we see that because C1, C24, and C3 are in series with each other, the total charge is the same as the individual. So Q1 is the same as Q total. Q24, the charge in the combination of 2 and 4, is the same as Q total. Q3 is the same as Q total. So we come back here and we make use of this information where Q1 equals 2.48 e to the minus 5. Q24 equals 2.48 e to the minus 5. And Q3 equals 2.48 e to the minus 5. But what we really wanted was Q2 and Q4. Now we know that Q2 plus Q4 equals 2.48 e to the minus 5 because when capacitors are in parallel, the total charge equals the sum of the individual. So how might we get the total charge, the charge Q2 and the charge Q4? Well, we make use of some of the information that we know here, and that is we jump to part D, where part D asks us to determine the potential difference. And here's what we do. Delta V1 will be given as the ratio of Q1 over C1. When we use the value of Q1 and the capacitance C1s, we get a potential difference across C1 of 6.2 volts. Next, delta V24 is the ratio of Q24 over C24. Again, using the numbers that we calculated above, we can determine that delta V24 equals 1.65 volts. But because C2 and C4 are in parallel, it is going to be true that delta V2 equals delta V4, which equals delta V24. So here we determine that delta V2 is 1.65 volts. Delta V4 is 1.65 volts. Last, delta V3, and we will come back up here in just a moment. Delta V3 is given as the ratio of Q3 over C3. We plug in the values that we have, and we get delta V3 is 4.13 volts. Okay, now let's come back over here to Q2 and Q4. Q2, we know, is the product of C2 times delta V2, which we obtained here. And so we are immediately able to get a value of Q2, which is 8.27 e to the minus 6 coulombs. We do the same thing for Q4, C4 times delta V4, and we get a value of 1.65 e to the negative 5 coulombs. And it will be true that if we were to add Q2 and Q4, we should get 2.48 e to the minus 5, provided we haven't made too many rounding errors. Okay, so we have obtained everything we were asked for: Q1, Q2, Q3, Q4, delta V1, delta V2, delta V3, and delta V4. We've effectively solved the problem. Next question. In question 7, we are told the following. A parallel plate capacitor with vacuum between the plates is charged by a battery, and here our delta V is 12 volts, storing a magnitude of charge equal to 5 microcoulombs. The battery is then removed. Now remember from our lecture, when the battery is removed, Q remains constant. And therefore, throughout this problem, Q, no matter what we do with our capacitor, provided we don't reconnect it to the battery, will be constant and equal to 5 microcoulomb. Anyhow, after the battery is removed, a slab of porcelain with a kappa value of 6 is inserted between the plates. We are asked to determine the following quantities. First, we're asked to determine the capacitance of the capacitor before the dielectric was inserted. Well, here we know nothing about the area or the distance of separation, but what we do know is that the capacitance is the ratio of Q naught over delta V naught. We use our numbers, Q naught 5 microfarads, delta V naught is 12 volts, and we get a value of 4.17 e to the minus 7 farads. In part B, we're asked to determine the capacitance after the dielectric is inserted. And of course, we know that it's going to go up by a value of kappa. So 6 times, which is the dielectric constant, 4.17 e to the minus 7 farads equals 2.5 e to the minus 6 farads. In part C, we're asked to determine the charge after the porcelain is inserted. Well, here, of course, Q is going to be constant and therefore does not change and remains 5 microcoulombs. Oops, I think I said farad here, but of course the charge is in microcoulombs. I'm not sure if I said farad. Okay. Part D, the potential difference after the porcelain is inserted. Well, here we know that C prime will be the ratio of Q prime over delta V prime. Now our Q has to remain constant, but our delta V prime is not constant. So because we already determined that it's going to be 6 times greater, to get delta V, we simply solve delta V prime equals Q naught times C prime. And by the way, C prime is 2.5 e to the minus 6 farads. Well, what we find is that our delta V prime is equal to 2 volts. And another way that we can solve for this is if we write Q naught over delta V prime, and we know that delta V prime, actually here this is incorrect because delta V prime is Q naught over C prime. That's better. And this is Q naught divided by kappa C naught. Well, Q naught over C naught is the ratio that we're looking for with a kappa in there, and that gives us this right here is of course our V naught. So this is really equal to V naught over kappa. So 12 volts divided by 6 gives us the 2 volts. So however we decide to obtain it, we could have used the value here, 5 microcoulombs, the value here of C prime. So dividing Q naught by C prime to get delta V prime, that should give us 2 volts, and you can verify that this is true. Lastly, we're asked to determine the potential energy before the dielectric is inserted and after the dielectric is inserted. Well, I'm going to go ahead and use the expression 1/2 C naught delta V naught. Okay, there's a delta V. Delta V naught squared. And remember, there are 2 other expressions we can use, but I'm going to go ahead and just use this one here because I can plug in directly my numbers and get 1/2 4.17 e to the minus 7 farads times 12 volts squared, and that gives me 3, provided my numbers are correct, 3e to the minus 5 joules. After the dielectric is inserted, I have 1/2 C prime times delta V prime. And of course, delta V prime is now 2 volts. And so this is going to be, because I can rewrite this as 1/2 C prime. Well, C prime is 6 times C naught. Delta V prime is delta V naught divided, oops, I have to square this term, divided by 6, the whole thing squared. Well, if you look over here, this is going to be 6 squared, and one of these will be canceled, this will be canceled by one of these, and so I'm left with the expression 1/2 C naught delta V naught squared divided by 6. Well, this is nothing more than U naught divided by 6. So if I take 3 e to the minus 5 and I divide by 6, I can get a number which should equal, let's see, this is going to be 30 microjoules divided by 6 will give me 5, if provided my calculations correct, e to the minus 6 joules. So you can see what is happening here is that I'm getting a reduction in the potential energy between the plates when I insert the dielectric and remove the battery from it. Okay, last, question 8 says now everything is true. The delta V is 12 volts, the charge is 5 microcoulombs, but my battery is going to remain connected, which means that delta V will have to be constant. Okay, so in the first part, we want the capacitance, which of course is the same as we obtained in question 7, 4.17 e to the minus 7 farads. It's Q naught over delta V naught. B, C prime after the dielectric, same porcelain, kappa C naught, and we get the same 2.5 e to the minus 6 farads. C, determine the charge on the plates after. This time, see, the charge can vary because it's the delta V which must remain constant. So, looking at the expression here, where Q prime is equal to C times delta V prime, this becomes C prime times delta V naught. You see, because our delta V now has to be constant. And we get 3 e to the minus 5 coulomb. In part D, delta V prime equals delta V naught, which is equal to 12 volts. Lastly, in part E, U naught equals 1/2 C naught delta V naught. That gives us 3 e to the minus 5 joules. And U prime equals 1/2 C prime times delta V prime, which is 1/2 C prime, which is 6 times C naught, that's our C prime, delta V naught, oops, again, we've got to square these terms. I keep forgetting to square these terms. Okay, delta V naught squared, and we can write this as 1/2 C naught delta V naught squared times 6. And of course, this right here is U naught, so 6 times this quantity, 6 times 3e to the minus 5, is what we get for U prime, U after the dielectric, which means that the potential energy goes up. So when our battery is still connected, insert a dielectric, rather than have our potential energy go down, as in question 7, our potential energy is going to go up. And of course, that's because there's a greater potential difference between the plates of the capacitor, including a larger capacitance. Well, rather, it's not a greater potential difference, but rather a constant potential difference. Whereas in question 7, the potential difference went down, if you recall. Okay, well, this concludes the last question in the problem-solving session of Chapter 26. Until next time.